This video is a short tutorial of the saferplaces' cloud web platform. The platform is available online as beta version at the following web address, platform.saferplaces.co. This video tutorial describes the main characteristics of the platform and how easy and fast is running a tailored flood hazard and damage assessment simulation and inspect the final results. saferplaces platform can support multiple stakeholders and end users in designing flood climate resilient cities through the simulations of multiple mitigation and adaptation projects and scenarios. The intelligence behind the saferplaces platform integrates innovative FASTM-based flood hazard and Bayesian damage assessment models, able to provide results in real time exploiting the power of cloud computing. A first beta version of the platform is available and so far is active in 7 pilot cities: Rimini and Milan in Italy, Pamplona and Fuenlabrada in Spain, Cologne in Germany and Byron Bay in Australia. The cloud web platform doesn't require any software installation on the user's PC and it just requires a web browser. A global version of the platform is now available online with the possibility to activate saferplaces modeling tools for every city worldwide, exploiting open data made available through Google Earth Engine and Amazon AWS. The activation process is smooth and fast. Clicking on the global panel, the user has the possibility to select a specific study area in a city worldwide. In the right panel it's possible to display the extension and coverage of the DIM and LiDAR available worldwide with different spatial resolution. For example, let's now proceed to activate saferplaces for a small portion of Miami in the US in 4 easy steps. Firstly, the user can select the city's querying through the upper left box, then select the extension of the study area holding the Shift command and the mouse. In this demo version has been set a limitation in the extension that depends also on the spatial resolution selected. The user should resize the area until it become blue. In the third step, the user can select among the available spatial resolution of DIM and LiDAR dataset, finally can create the project. The procedure requires a few seconds and the generated cities will be available and ready to be used. As you can notice, the global version has been available for free with some limitations and reduced functionalities. Coming back to the main landing page, we now proceed in selecting one of the 7 pilot cities available. In this case we select the city of Rimini. The user should proceed through the login request, inserting name and email address in proper fields. The registration procedure generates automatically the new credential communicated by email. The user's credentials can be now used for the login and obtain the full access to the platform. The web application is composed of several task panes located on the left and a web mapping environment in the right. On the left, the user can select and activate different panels. Starting from the bottom, the Layers task pane displays the list of spatial layers generated by the platform and a set of preloaded data such as different backgrounds such as Google Satellite or OpenStreetMaps, the LiDAR of the study area and the polygon of the buildings. The group of layers named as river, rain, coast are initially empty and will be populated later by the outputs generated by the simulations. The first task pane, source scenarios, is dedicated to define multiple flood hazard scenarios related to pluvial, fluvial and coastal events. The user is free to generate whatever flood hazard scenario specific for the city of interest. The flood source scenario can be representative for historical or climate projection conditions. In particular, the user has now the ability to generate flood hazard and damage scenario in 5 different options. With the orange panel can set up a tailored and specific rainfall events characterized for example by a specific rainfall intensity in millimeters and duration in hours. With this option, the rainfall intensity is considered uniform for the entire study area. The checkbox inf is related to the possibility of activating the natural green EMT infiltration model. In this case we select a rainfall event with return time of 100 year characterized by a duration of 3 hours and intensity of 95 mm. For this scenario we activate the natural infiltration model. The checkbox damage activates the computation of economic damages together with flood hazard maps. In the section with yellow label rainfall event, the user has the possibility to define a spatial non-uniform rainfall event and simulate the hazard and damage. The spatial non-uniform rainfall event can be defined by either uploading a dedicated raster file with rainfall total amount in millimeters or drawing polygons across the study area as displayed. The user can define multiple polygons of rainfall areas with tailored total amount in millimeters. Gradually the number of polygons and total volume of rainfall is reported and updated in the scenario. In this case we have generated two rainfall spots of 90 and 60 mm for a total volume of less than 300,000 cubic meters. After a few seconds the users can display the flood hazard maps. For fluvial events the user has two possibilities to simulate riverine floods. Within the Azure panel the user can select a list of preloaded flood hazard reference maps to be used as benchmark for the GFI calibration and the generation of flood hazard maps at higher resolution. In this case we simulate an event of 100 years return time. In the blue section has been developed the possibility to simulate the flood hazard as a consequence of a specific volume of water released from one or more point sources. Clicking on the Draw checkbox the user activates a specific panel with the possibility to localize the point of release and define the volume. The source scenario panels display the number of points and total volume. In this simulation the users have defined 2-point releases characterized by 100,000 cubic meter each along the river channel. Lastly, in the purple section the user can set up multiple extreme sea level and M to be used in coastal flooding simulations. For example, we generate a coastal flooding scenario characterized by a return time of 100 year with climate projection RCP 4.5 for 2100, the extreme sea level is equal to 2.77 meters. Clicking in the Add checkbox the user can submit the generated flood hazard scenarios to the control panel for the process execution. For each scenario, in case you want to compute both hazard and damage, don't forget to activate the damage checkbox. In the control panel the user can run all the process clicking over the dedicated button, or just activating a single simulation. The single process starts and the user can follow the stage of processing. After a few minutes the user can display the first results related to water depth and damage assessment of the scenarios. The water depth and economic damages layers are generated and uploaded in the specific layer group available for rainfall, coastal and river sources. Through the Identify button the user can inspect the water depth value pixel by pixel or the economic damage building by building. Two other buttons are available in the top of the window. The first button allows the user to easily plot the water depth for a specific section simply drawing a line on the water depth generated by fluvial, pluvial or coastal scenarios, as displayed in the video. The second tool permits the user to compute and visualize for each depression the amount of water present related to the specific rainfall event intensity. In this case, for example, the selected depression is 100% filled with a volume of around 60,000 cubic meters and a spillover of 5,000 cubic meters. This information could be very helpful to support the design of mitigation measures in the selected areas, in case the users have already available flood hazard maps provided, for example by hydrodynamic numerical models, remote sensing data or other sources. It's possible to upload it in the platform and compute the flood damages at building level. In the Damage Model task pane, the user can upload a water depth file, visualize the map in the platform and then compute the economic damages for each building. Finally, the user can download the generated output as GeoTIFF files just with right-click over the layer of interest. The saferplaces platform has been designed to support users in designing and assessing mitigation measures. Through specific tools the users can design and assess the flood risk mitigation capacity of different mitigation measures, such as flood barriers, retention water tanks and green area development in urbanized and sealed areas. In this example, the user defines a physical flood barrier able to contain coastal flood hazard and consequently reduce economic damage. The user is free to draw the geometry, the extension and the height above the ground of the barriers. In this example, we generate artificial dunes with height 3 meters, and we are able to quickly map flood hazard and damage assessment considering this adaptation and mitigation project for the city of Rimini. The second mitigation measure, that can be designed and tested by the platform, concerns the localization of a retention water tank able to reduce the volume of water accumulated into the depression during a pluvial event. The user can define multiple water tanks across the cities, characterized by a specific volume of water. After that, he quickly maps the effects in terms of reduced flood area extent and water depth, and also in terms of reduced economic damages. The third option embedded in the platform, for reducing flood risk in urban areas, is related to the possibility to modify and change the soil sealing permeability. This basically entails urban regeneration and urban green area development. The user can select the polygon's area where the change of soil sealing is expected and quickly test the effectiveness in terms of flood hazard and damages. The last mitigation available in the platform consists in the possibility of assigning specific damage mitigation options to each building. For example, the adoption of flood barriers and transforming buildings in order to be more resilient towards flood damages. The user can select the appropriate mitigation measures and simulate the effects in terms of damage reduction. A dedicated dashboard panel has been developed with some basic functions. The dashboard will be enriched soon with new functions and tools for supporting the users, in cost-benefit analysis and a fast comparison, among different climate and mitigation scenarios. So far, the user can draw on the map specific polygons representing the area of interest of the analysis, and plot histograms related to total economic damage. In this example are reported the total damage for the city of Rimini related to coastal flooding in current and mitigated future climate scenario. For more information related to the Safer Places project, we recommend to visit our website www.saferplaces.co, where you can be constantly updated about Safer Places outcomes and news. In particular, in the section Papers, you can find the articles recently published on scientific peer-reviewed journals about the hazard and damage assessment models embedded in the cloud web platform. Thanks for your attention, and please follow us.